Homework 7, problem 2. Find the gyromagnetic ratio, which is the ratio of the magnetic moment to the angular momentum for a spinning charged donut. And so here's an example. We have a donut that is spinning around the axis of symmetry here. It has the total charge Q, and it has the total mass M. And we're asked to find its ratio of magnetic moment to angular momentum. First, we might as well write down what angular momentum is. Angular momentum is going to be the moment of inertia, I. Where here we have to be careful, this is moment of inertia, so maybe I am I, times the angular momentum in vector form, like that. The moment of inertia for any object is just the integral of the mass of the object times its distance from the center. For a thin hoop, it's all essentially at that same distance. That distance we will call little r. And so the moment of inertia, mi, is going to be the mass times little r squared. And so the angular momentum then is the mass times little r squared times omega times k hat. We'll just define this as the z direction. Okay. So define that as the positive z direction, and so the omega vector is in the positive z direction. Now the magnetic moment is not that much different to find. For the magnetic moment, we define the magnetic moment as the current I times the area, the normal vector of the area for some current loop. Now the area that we're looking at is the area of this hoop, and so this area is fairly easy. This is pi times r squared. The normal vector is fairly easy. That's just going to be k hat. And so now we have to figure out what the current is. So the current is a little bit more tricky, but not too much. So let's look here. Let's write down, if we look at the charge that goes through some small area there, right? We can write the current I is integral d2x n hat dot j, and j of course is rho times v, and n hat for us is going to be in that direction, which is going to be the direction of rotation, so it's going to be the direction of v. So n hat dot v, and so this is integral d2x of rho times n hat dot v, which is just going to be the speed v. So this here is just going to be the speed v, which of course we know is omega times r. So now we have to figure out what rho is. Well, rho, if we say it's evenly distributed, rho, if it's evenly distributed, will be whatever this little area here is, so this a bar, times the length around, which is going to be the circumference, so 2 pi r. And so rho is going to be the total charge divided by this a bar times the circumference, 2 pi little r. The integral d2x of rho is going to get rid of this a bar, right? So this I is going to be, so this is an integral over the area, so it'll be the area I'm going through, so I'm going to get a bar from that. I'm going to cancel this a bar down there. So I get q over 2 pi r times omega r. So the r's will cancel. So I get omega q over 2 pi is the area. Plugging that back in to our formula up here, we're going to get that the magnetic moment is q omega over 2 pi times pi r squared times k vector. And so a little bit of simplification is that the magnetic moment is pi's cancel, so this will give q over 2 times omega r squared k vector. Now, the final thing, which is very easy, is if we're looking for the ratio of the magnetic moment to the angular momentum, the gyromagnetic ratio, we just take this and divide it by that. The omegas cancel, the r squared cancels. They point in the same direction, which is going to be true as long as I had a uniformly charged object. When it spins, the current will always be in a loop in the same direction as the angular momentum. And so that was going to need to be the case. So in the end, we find that this guy here is going to be simply equal to, so again, let's make them vectors so that division, or let's make them magnitude so that division makes sense. Q over 2 times the mass. And that is it.